The universal law of gravitation was discovered by Isaac Newton, and it describes the gravitational force between objects as a function of their masses and their separation distances. Gravitational force is always attractive. In our current understanding of physics, there is no such thing as anti-gravity. Recall that according to Newton's third law of motion, if m1 pulls on m2, then m2 pulls back on m1 with the same size force but in the opposite direction. Any difference in their masses is irrelevant. The universal law of gravitation states that the gravitational force is proportional to the product of their masses and inversely proportional to the square of their center-to-center separation distance. Here, the mass is represented by m and the separation distance by r. The more massive either or both of the objects are, the stronger the gravitational force. The greater their separation distance, the weaker the gravitational force. The gravitational constant g is a proportionality constant that has been determined experimentally to have the value shown. This law of gravitation is an example of what are collectively known as inverse square laws. The force weakens inversely as the square of the distance. This is how it works. On the surface of the Earth, an astronaut would have a force equal to her weight. That is, at 1 Earth radius, the gravitational force on her by the Earth is 1 Fg. At 2 Earth radii, the gravitational force goes down by a factor of 2 squared or 1/4 Fg. At 3 Earth radii, it's 1/9 Fg, etc. The gravitational force weakens rather quickly with increasing distance. On the other hand, the gravitational force increases rather quickly as the distance decreases. Consider the following scenario. Suppose the Earth were being compressed to a smaller volume. Assume that the Earth retained all its mass during this process and it was only becoming denser and denser. Suppose too that the astronaut was able to somehow maintain a distance of 1 Earth radius from the Earth's center while this was happening. Resorting to the equation, one can see that since neither mass was changing, and since the center-to-center distance would not be changing, the gravitational pull on the astronaut would always be the same. Even if the Earth were squeezed until it formed a black hole, the gravitational pull on the astronaut would always be the same. Now let's imagine altering the previous scenario. Suppose the astronaut were continually standing on the surface while the Earth was slowly compressed under the astronaut's feet. The center-to-center separation distance would then be decreasing. The gravitational force on the astronaut would continue to increase. Before the Earth were small enough to form a black hole, the astronaut would be squeezed by gravity to a gooey puddle 1 atom thick on the surface.